Hello guys. So today in the past few videos we looked upon divisibility and we learned few properties of divisibility, the bounding property, the subtraction property, and uh, we also learned the linear combination property. So but those all the properties were applicable when the remainder was zero. Today, our topic is Euclid's lemma, Euclid's division algorithm, and we will ask an important question: what happens when remainder is not zero? In the previous videos, we looked upon when the remainder is zero. So today, we will look upon what happens when the remainder is not zero. So Euclid's lemma is also sometimes it is known as division algorithm as well. And to be honest, like if you mastered this topic, your whole number theory, GCD, LCM, Bezos identity, modular arithmetic, and even polynomial irreducibility, these all topics become very easy, right? So let's look at the formal statement of this Euclid's division algorithm, Euclid's lemma. What it says: it says given integers a, where a is a dividend, b, where b is a divider and is greater than 0, which means non-negative divisor, then there exist quotient q and remainder are such that a can be written as a is equal to bq plus r. So what it says is, if there is some number, let's say 5, and you are dividing it with 2, this number which is written inside, which is divided, is known as dividend, and this is known as divisor. Okay, so 2 to the 4, and then you get a remainder of 1. Now it says that you could write this dividend 5 as 2 into some integer plus some remainder, and here some integer is 2 and remainder is 1. Same goes for any other number you divide. Let's say you try to divide 3 with 17. Okay, so you are dividing 17 with 3 5s are 15 and you get a remainder of 2. Then you can write 17 as 3 into 5 plus 2. So what this says is there always exists integer q and remainder are such that you could write dividend and divisor as such. But here is an important constraint, and that is that remainder must be greater than or equal to 0 but less than b. Like it would always be less than divisor. It would be greater than 0. Remainder would always be greater than 0 and less than divisor. Divisor is 2, and you can see that 1 is less than 2. Similarly, divisor is 3. You can see that 2 is less than 3. Remainder will always be less than divisor. This is an important constraint here. And if I want you to write down 32 using division algorithm, you can write it like such. 32 is you divide 32 with, let's say, 2, and then you got 2 1s are 2, and here you have it's remainder 0. Let's try divide by 5 ones of 5 6 30, and then you get a remainder of 2. So you could write it as 5 into some quotient, which is 6 here, and some remainder, and that remainder is greater than 0 but less than 5. Okay, this is how Euclid division algorithm. You can also write it as 5 into 5, which is 25, and then you get a remainder of 7, right? You could also write it as 5 into 4, and you will get a remainder of 12. But these both are wrong, because here remainder is greater than divisor, and that's not how Euclid what Euclid division algorithm says. It says the remainder must be less than divisor. That's why you could also write them like such, but that would not follow division algorithm. Now, with the help of this division algorithm, Euclid's division algorithm, you can divide the whole integers into 2 or 3 cases. Let me show you. So if you take any number, let's just say we are taking 32 and we are dividing it with 2, okay, 2, and then you take any other number, let's just say 47, and you divide it by 2, and let's say you take any other number, let's say 15, and you divide it by 2, and let's say you take any other number, you divide it by 2 as well, okay. Let's see what happens. 2 ones are 2, and then you bring 2 down, and 2 6 are 12, and you get a remainder of 0. Now let's write it down as such using Euclid's algorithm. 2 into 16 plus 0. Just look at the remainder, okay? Just look at the remainder because we will deduce something really beautiful from here. 2 2s are 4, and then you take down 4 7, and 2 3s are 6, and you get a remainder of 1. We could write it as 2 into 23 plus 1. Just look at the remainder. Just look at the remainder. And then again 2 7s are 14, and then you get a remainder of 1. You could write it as 2 into 7 plus 1. Just look at the remainder again. And then again 2 12s are 24, and you get a remainder of 0. Just look at the remainder again. 2 into the 12 plus 0. Did you notice something? You can only see the remainder is either 0 or 1. Why is that? Earlier I told you that this remainder will always be less than divisor, okay. So here divisor is 2, here divisor is 2. So you take any number, any integer, let's say 9999999, you take any device, any number, its remainder will always be less than 2. Its remainder will always be less than 2. So I can deduce from here that the whole set from 1 to infinity of integers, I can divide them as, I can divide natural numbers from 1 to infinity. I can divide them in 2 cases, such as 2q plus 0. Either the remainder will be 0, either remainder will be 1. You saw it. Either it is 0, either it is 1. So either it is gonna be 0, either it is gonna be 1. This doesn't look nice. Let me remove this. Okay, so either it is gonna be 2q plus 0, either it's gonna be 2q plus 1. Similarly, if I ask you, if I want you to divide in the modulo 3, which means modulo means dividing by 3, then you would get 3 cases: 3q, 3q plus 1, 3q plus 2, because it can never be 3q plus 3 or 3q plus 4, because the remainder is greater than divisor, which is not possible, okay. I mean, it is possible, you could write it in the way, but that would not follow Euclid's division algorithm. And if I ask you to divide natural number into modulo 4, then you can divide it as 4q plus 3, 4q plus 2, 4q plus 1, and 4q, right? Same goes for any other natural number. This technique is really useful in using while solving the problem. We would use it a lot, and we would now see few questions in the next videos on this topic, Euclid's lemma. Thank you.